Bonjour. This lesson focuses on the problem of correlation, simple correlation, linear correlation between two quantitative variables. The presentation lasts about 30 minutes. The first part of this presentation requires no special prerequisites. It requires only to know the concepts of mean, to measure the central value of a distribution, and the concept of variance to measure the dispersion. The end of the presentation requires to know the concept of statistical test and in particular how to use the student t-test. Let's start immediately with a concrete example. The list of numbers you see on this table are the results of analysis of a series of 30 sera assayed to measure a parameter by a laboratory technique that I call technique number 1. I will comment neither the technique itself or the parameter units in order to not perturb the demonstration. The only interesting thing to watch for now is that it is a quantitative variable with values ranging from a minimum to a maximum. Its distribution could be represented by an histogram. Here is now a second list of blue-colored numbers that are the results of the analysis of the same serums by a second technique. This is still a quantitative variable expressed by a number, and you will notice that the units are not at all the same as those of the first technique. We now have two sets of values of two quantitative variables. Each serum was tested twice. Both series are called paired series. And the question is to know whether the two techniques give similar results. Are they consistent? Are their results correlated? For example, if a result is high with the technique number 1, is it as high with the technique number 2? If a result is low with the technique number 1, is it rather low with technique number 2? But you see immediately the difficulty by watching the numbers that are too numerous to be compared and which, moreover, are not distributed according to the same scale. Then, in order to present this data more clearly, we will build a two-dimensional graph to locate each pair of values of both variables. We will choose, for example, to represent on the x-axis the range of the results of technique 1 and on the y-axis the results of the technique 2. We might as well make the reverse. In this example, it doesn't matter. Then, for each pair of values, we will plot a point whose the x value is the result found by the technique 1 and the y value is the result found by the technique 2. Here is plotted the first point for the serum whose results were respectively 9.3 and 0.16. Then the second point corresponding to the values of the second serum, 13 and 0.18. The third point for the third serum, and so on. We finally get a kind of cloud made up of 30 points corresponding to the 30 couples of observed values. What can one read on this graph? It gives us the impression that, roughly speaking, when the values of technique 1 are high, the values of technique 2 are also high. But this is not true for all the points. Some of them, such as the one shown by the red arrow, has a value of y, what is among the highest, while the corresponding value of x is not far from the mean. On the opposite, the point shown by the blue arrow corresponding to the lowest value of x is not the lowest value of y. So, we can say only for the moment that there seems to be some relationship, some correlation between the values given by these two techniques. Let's see other examples of cloud of points which one could have obtained with other values of x and y. For example, this cloud made up of points obliquely oriented and very tightened, what indeed suggests a strong correlation. This second example on the right, where the points are scattered, suggests a poor correlation. And in the worst case, the example in bottom on the left suggests a complete lack of correlation. For any value of x, we find any kind of value of y and vice versa. There is no link between x and y. It is also possible to obtain such a cloud of points as the one shown on the bottom right, where more the values of x are high, more the values of y are low. This suggests a strong but negative correlation. In the previous examples, we have visually interpreted whether or not a link between two quantitative variables. It was easy but a little rudimentary. Now we will try to measure in a mathematical way the strength of the link, the strength of the correlation between two quantitative variables. As we could summarize the normal distribution by the calculation of the mean and the variance, we would want to summarize this cloud of points by drawing a straight line. A line whose equation would be y equal r plus bx, where b is the slope and r the intercept. But is the line drawn of this graph the most appropriate? I could have proposed as well this other line in blue. Then the question which arises is how to draw the most appropriate line in order to resume correctly the cloud of points. What we will do is to proceed in a way by trial and error by looking for the line which is closest to all the points. It is not so easy because some of the lines are closer to certain points while moving away from the others. We must find the line which presents the best compromise, the line which fits at best with the points. A method consists in calculating for each selected line the vertical distances from all the points to this line. And we will choose the line which on average is closest to the points. In fact, one does not compute the distances but the squares of the distances, because as you can see, some points are above the line, thus with positive distances, and some points are below the line, thus with negative distances. The sum of these distances tends towards 0. To cancel this effect, the square of the distances is taken. And the best line, the best adjusted line, is that whose the sum of the squares of distances is the smallest. It is called the least square line. The mathematical calculation of the parameters of this line is very complicated, and you will undoubtedly do it never. This calculation is beyond the scope of this lesson, and you have just to know that all softwares that draw scatters from two sets of numbers, including Excel and PowerPoint, draw automatically the least square line, and they calculate the parameters slope and intercept. In order to illustrate this research process of the least squares line without using mathematics, I propose this small graphic analogy. Here is a scatter plot deliberately reduced to a few units to see clearly the demonstration. I draw a straight line which approximately fits with the points. I draw the vertical distance of each point to this line, and then I will square each of these distances. I do that graphically by drawing along each segment of distance the squared area whose this segment is the side. Here is the square of the distance of the first point to the line. I repeat the same operation for each distance, and finally I pile the squares areas together, what gives us at the bottom right an entire area which illustrates the sum of the squares of the distances of each point to the line. Now let's draw a second straight line. I repeat the same operations by drawing the squares of the distances of each point to the line, and at the bottom right I pile these squares to visualize their sums. And now we can compare the areas corresponding to the lines 1 and 2. And it's easy to see that the sum of the squares distances to the line 2 is smaller than that of the line 1. Thus, line 2 fits better. Let's try a third line. Let's draw the area of the sum of the square distances, and let's compare it to the previous areas. One can see that it is smaller than the first, but not really different from the second. We did not gain much by plotting this third line. Let's see a last line and its area of the sum of the squares. You note that the sum of the square distances to this line is the smallest of the 4 lines tested. And if we did not find a smaller area, we can say that the line 4 is the least squares line. This line is that which fits best with the cloud of points. What we have just done here with a graphic way is strictly similar to the mathematical algorithm which computes the parameters of the line by minimizing the sum of the squared distances. Let's come back to the first example of the 30 couples of results of two laboratory techniques. After computing the numbers to minimize the sum of the squares residuals, as we call them now, we get the parameters of a line whose the slope b is 0.075 and the intercept a 0.0714. With these parameters, which have been calculated automatically from the data entered in PowerPoint or in Excel, one can draw easily the least squares line. At present, we know how to calculate the parameters and to draw the least squares line. Now, we will try to quantify the level of the relation between two sets of values. We have seen that the points of some clouds could be more or less tightened around the line, that the line could be more or less oblique. To quantify the level of correlation, we have to compute the correlation coefficient, also called Pearson correlation coefficient. The correlation coefficient, which is usually called R, is a parameter. We can calculate it. I avoid generally the use of too much mathematical formulae, but in this case you won't escape to the formula which is hidden behind this dark screen. Before I reveal it, you will know that I show it to you only so that you well understand what is a correlation coefficient. There is nothing to remember, and you'll probably never do the calculations manually. Here is the formula. At first glance, it looks like a monster, but examine it carefully. First of all, in the denominator, under the square root sign, we have the product of two terms. The first term, sum of x minus min x squared, is the sum of the squares of the distances between each x and the mean of x. And you will recognize the numerator of the variance of x. In the same way, the second term sum of y minus min y squared is the sum of the squares of the distances between each y and the mean of y. And you will recognize the numerator of the variance of y. Now let's have a look on the numerator of R. Sum of the product of x minus mx by y minus my. It is the sum of the product of the distances of each couples of values to their mean. This term is the numerator of a parameter called the covariance xy. Thus, in another way, a correlation coefficient between two variables is simply the ratio of covariance by the square root of the product of the two variances. Here I present you another formula of the R coefficient. This formula, strictly equivalent to the previous one, is supposed to be simpler. I show it to you because it is written in all the textbooks. I like it less than the other one because it is less explicit, but its advantage is to allow easier manual calculations if you don't have a computer. But the best way to calculate a R coefficient is to use a software like Excel. We have entered in the two columns A and B the 30 couples of techniques results. And you have just to enter, in any case of the spreadsheet, the command equal correl and between brackets the first set of values A2 colon A31, comma, the second set of values B2 colon B31. I show you below the translated syntax for French version of Excel. And after entering the function, one obtains immediately the R value equal to 0.83 in this example. Thus, the calculation of a R coefficient should not be difficult. What needs your attention is rather the interpretation of its results. First of all, the values of the correlation coefficient range between -1 and +1. A correlation coefficient which would equal to 1, would show a perfect correlation where all the points would be aligned. On the top right, a coefficient equal to 0.4, for example, indicates a weak but real correlation. In the bottom left example, the correlation coefficient is equal to 0. The slope of the least squares line is horizontal. There is no correlation between the values x and y. At last, a value of minus 0.9, close to minus 1, shows a strong but negative correlation. The last question to solve is to know beyond which value of R one can affirm a true correlation, or in another way, how to measure the significance level of a correlation coefficient. For that, it is necessary to use a statistical test. Let's come back to our example where we found the correlation coefficient equal to 0.83. Is this value significant enough to affirm a correlation as it is supposed by the graphic picture? As for all statistical tests, we begin to make hypotheses. The null hypothesis, H0, is the correlation coefficient. We called here it rho because it concerns the theoric population. This coefficient is equal to 0. There is no correlation. Alternative hypothesis, H1, the coefficient rho is different from 0. In our example, where we guess if there is a link between the results of two laboratory techniques, hypothesis H0, there is no link between the results of the two techniques. Hypothesis H1, there is a link between the two techniques. The test itself is not very complicated. It is a simple student t-test where the value of R is compared to 0. The statistic t is the ratio of R minus 0 divided by the standard deviation of R. The formula of standard deviation of R is quite simple. Square root of 1 minus R squared divided by the number of couples of values minus 2. Then the value of t observed is compared with the values of the t table at the line corresponding to the n minus 2 degree of freedom. Back to our example, we have R equal to 0.83, the number of couples of values n equal 30. We calculate the standard deviation of R, SR, equal square root of 1 minus 1.83 squared divided by 28. That gives 0.11. Then we calculate the statistic t, 0.83 divided by 0.11. That gives 7.5. We look in the table of t at the line of 28 degree of freedom and we obtain a p-value of 10 power minus 6. For those who don't want to make these calculations, I show you here the syntax used with the Stata software. PWCORR, then the names of the two variables, here named take1 and take2, comma, SIG to get the statistical test. Stata computes exactly the same results as we expected. In conclusion of this test, we will say that there is a strong correlation between the results of these two techniques with a 0.83 coefficient. This correlation is statistically very significant, with a risk of error lower than 1 for a million. How to interpret all the results given by a correlation analysis? You notice that this analysis gives two parameters, a coefficient R, ranging between -1 and +1, and a p-value. The R coefficient gives the strength of the link. More R is close to 1 or close to -1, stronger is the link. More R is close to 0, weaker is the link. While the p-value gives the significance level of the test. That's to say, the confidence with which it can be said that the link exists. You note that these two concepts are radically different. In this example, the R coefficient, 0.9 is high. The correlation seems to be strong. But the sample size is small and the result of the test with a p-value larger than 0.05 is not significant. We cannot assert that the correlation is certain. Conversely, in this example, the correlation with the R coefficient of 0.3 is not strong, but the sample size is large, and the test shows a significant correlation. We can assert with a low risk of error that there is a link between the variables, but this link has a weak intensity. Let us examine now the conditions we need to apply a correlation test and its limitation. First, as for any statistical test, both variables, x and y, must be random variables. In our example, the results of each laboratory techniques for each serum tested must be independent from each other. Second assumption, the association between x and y must be linear. What does it mean? If we take the example of this figure, it is obvious that there is a strong relation between x and y. But this relation is not linear. It looks like a reverse parabola. If we calculate the least squares line and the linear correlation coefficient, we would obtain a slope b and a R coefficient close to 0. Whereas there is an obvious correlation. But in this case, one should use another correlation model which would better fit with the data. In the example shown on the right side, there is a correlation and maybe we will get a significant linear correlation. But the power of the analysis would be low, and above all things, you see that the straight line is not at well predictive. Here again, one should use another model. In the example shown on bottom left, the first part of the graph shows a linear correlation, but beyond a certain value of x, the values of y do not increase anymore. There is a kind of saturation phenomenon, which is common in biology and in the life sciences. Thus, the slope of the line and the correlation seems to be weak. But if we limit the study to the lowest values of x, if we examine only the linear part of the curve, then we can observe a strong correlation. A third condition, which is not easy to understand, states that the conditional distribution of one of the variables, no matter which one, must be normally distributed and homoscedastic, what means with a constant variance. What does this assumption mean? For example, for a given value of x, all the corresponding values of y must be normally distributed. And all the distributions of y for each value of x must have the same variance. All this is very theoretical and of course unverifiable in practice. To illustrate this concept, have a look on this graph. For most of the values grouped in the bottom left of the graph, it is obvious that there is no correlation. But the two extreme values, called outliers, are of a very heavy weight in calculation of the slope and of the R coefficient, and the result can show a false correlation. To finish with these assumptions and limits, let us come back on a condition seen in the first paragraph, the independence between x and y. There is some situations where x and y are not independent. For example, if you consider a phenomenon y which is linked to the time which passes, considered as x variable, for example, the frequency of the occurrence of an infectious disease along the time. On the y-axis, we plotted the number of cases and the days on the x-axis. And the question is there an increase of the number of cases with the time? But as we study here a transmissible infectious disease, it could be supposed that the number of cases which occurred a given day is not independent from the number of cases which were present the day before or even 2 or 3 days before. It is said that there is an autocorrelation between these two variables. Thus, if we want to study the link between time and the occurrence of this disease, one should use other methods more sophisticated than the simple linear correlation to avoid this problem of autocorrelation. These methods are part of that we call time series analysis, what is out of the scope of this lesson. I would like to finish this lecture with a recurrent problem that arises in the discussions about correlation. Does the identification of a correlation involve a causal link? For example, if you demonstrate there is a correlation between the time passed daily by people watching TV and the body weight of these people, does this prove that time spent sitting in an armchair doing nothing is the cause of overweight? Probably no. Moreover, at the opposite, the overweight could be the cause of overwatching TV. Let's take a last example. This study shows a strong correlation between the amount of sunscreen consumed by country and the number of skin cancer in these countries. Are the sunscreen products carcinogenic? What could be possible? Why not? But you know indeed that sunscreen is used when people are exposed to the sun, and also that a too long exposition to the sun is a frequent and well-known cause of skin cancer. Thus, the relation shown on this graph between sunscreen and skin cancer is strong, it is real, but it is not causal. So, in conclusion, I would strongly advise you to remember this assertion: the demonstration of a correlation, as strong it is not at all the proof of a causal relationship. If you want more precisions about the concept of causality, go to my lesson entitled Causality. I have finished this lecture on the simple linear correlation. There is other methods to analyze a correlation, like the Spearman rank correlation test that computes the ranks of the values x and y rather than the values themselves. I propose a lecture on this test. Another of my presentations concerns the linear regression. So, I tell you, à bientôt!